So we have seen in this video lecture, we have seen how to translate the definitions of convergence of Borel function into the world of probability spaces and random variables. So this is convergence of random variables. Then we saw that convergence in LP, unlike general measure spaces, when the measure space is a probability space, convergence in LP implies convergence of the integrals. Then we have seen the definition of convergence in distribution, and we saw an example of how geometric with a small parameter, so geometric with a small parameter, so they become larger and larger, but if now we divide them by n to compensate the fact that they are becoming larger and larger, so what we are doing is we are making them less and less discrete until in the limit they converge to an exponential variable. Here's another example to illustrate why we do not require convergence when on the points where the cumulative distribution function of the limiting variable is discontinuous. And here's a very simple example. What is xn? Xn is we toss a fair coin, and with probability 1/2, we're going to declare xn to be 1. And if it comes up heads, if it comes up tails, which also has probability 1/2, we declare xn to be equal to 1 over n. And so we can write informally xn equal 1 over n with probability 1/2, or it will be equal to 1 with probability also 1/2, which means the cumulative distribution function of xn is this function here. Here's 1, here's 1 over n, here's 1/2, and here is 1. So this is the cumulative distribution function of the variable xn, and well, the claim is that this converges to the only obvious thing that it would be reasonable to say it converges to. It will converge to a random variable that with probability 1/2 takes value 1, and with probability 1/2 takes value 0. That's what happens when we take the limit and send n to infinity. So the only thing in this whole line here that depends on n, the only dependence on n here is this number, which is getting smaller and smaller. This is the 1 over n. And so here's the cumulative distribution function of the variable xn. And so we expect it to converge to a Bernoulli random variable with parameter 1/2. What does the cumulative distribution function of a Bernoulli with parameter 1/2 look like? It looks like this. It is 0, then it jumps to 1/2, then it jumps to 1, 1, 1/2. And now we ask, does this converge to this? And if we check whether it converges or not, we'll see that, well, for any point that we fix here, this is always 1. So yes, of course it does converge. Here's the same point down here. It is always 1. Yes, so constant sequence equal to 1, it does converge, yes. If we look at this point here, even, we're here, this is constant equal to 1, so it's still converging. If we fix the point here to be 1. If we fix any point smaller, then it also converges because here it is 1/2 and here it is constant equal to 1/2. Oops. It's not exactly constant equal to 1/2. If we fix this point here, which is here we're getting 1/2, and here we eventually will get 1/2. We just have to wait until n is so large that this interval is to the left of this point, and so it will be 1/2 from that point on. However, there is one point here that will pose us problem. It is exactly this point here, 0. Because then this cumulative distribution function on 0, it will be always equal to 0. So it will not converge to 1/2. So we do not converge to this point here. So what we are saying is f xn is converging, or fxn of t is converging to fx of t for all t different from 0. But it's okay to not to converge when t equals 0, because when t equals 0, this is a point where fx is discontinuous. So this would be an example that explains why we do not require convergence in points where it is discontinuous. So basically what we have as distribution function is a curve that jumps and jumps again, and if this jump is moving left, it's reasonable not to require the function at this point to converge. And finally, this may be more convenient in many occasions, and this is the more proper definition of what it means for some distributions to converge. It is for using test functions. So we say that the family of random variables, it's a theorem because we have already defined what it means to say that what it means to converge in distribution to another random variable. And the theorem saying if and only if, so it is equivalent to having this expectation converge for every function f which is bounded and continuous. And this can be a convenient formulation sometimes. We're not going to see examples of this theorem right now. It's just some useful theoretical tool to keep in mind that this is another way to represent convergence in distribution. It has to be for every f. So it is not that easy to have this convergence, but it turns out this is equivalent to converging in distribution. Or let us give an example. Suppose xn converges almost surely to x. Does it imply, can we conclude that xn also converges in distribution to x? Well, yes, and we can use this theorem together with bounded convergence theorem, because xn converging almost surely to x, this implies that, well, there is a set, there's an event whose probability is 1, where xn converges to x, and because a function f is continuous, this means f of xn will converge almost surely to f of x. And now because we're assuming f is bounded, then we can use bounded convergence theorem. It's one of the corollaries in chapter 5, the corollary of a dominated convergence theorem. So this would be bounded convergence theorem. That's because we're assuming the functions f to be bounded. So this implies that expectation of f of xn converges to the expectation of f of x. And this, since this is true for every x, we can conclude that xn converges to x in distribution. So this is one way we could use in practice this convenient formulation. It can sometimes be more convenient than the original definition of convergence in distribution. We're not going to see a proof of this theorem. It's just something to keep in mind, something to be aware of that can be useful at some times. So this concludes this video lecture.